So Bernoulli's equation is actually the dynamics of a fluid. So when the fluid is flowing, it tells you how fast the fluid is supposed to flow. If it's flowing at this condition here, and you want condition over there, a different side. So if you think about it as an extension of that continuity equation, that's where we're going. The continuity equation only accounts for well, there's a change of a cross-sectional area, and you cannot change that vertically, right? That incurs some change of gravitational potential energy, but horizontally that's okay. All right. So if you want to know if water is flowing over here, say in your basement, water comes in the main pipe in your basement and flows out of one of the faucets in say on the second floor bathroom. So how does that actually work? So you can understand things like the fluid has changed height. It also probably has changed cross-sectional area or the velocity it flows, and also the pressure. I'm pretty sure the pressure is different, right? Pressure is different between the basement and the second floor. So let's consider this a fluid. So here's a fluid. We'll call this a flow pipe. It's not an actual pipe. So I'm trying to do something like the cross section is changing, but it's only changing very gradually. A pipe or two. So its idealized flow is basically just kind of a section of the overall fluid that's flowing. And the nice thing about this section is fluid does not flow out of the section, neither does it flow into the section. So it's like following an overall trend. Maybe there's just a stream that changes, it narrows down at places, then widens up and narrows down again and maybe widens up. And you just take a small sliver stream out of that whole stream of water, say a river, and that kind of follows the overall change of cross-sectional area between the banks. So water does not really flow out, neither did it flow into this tube or the pipe, so that we can study this more easily. And in a more well man-made structure, you can imagine these are just tubes, pipes, physical pipes, tubes that restrict the flow of fluid. All right. So we'll call this place here's 1. Here's a 2. Okay. So let's establish things that we're interested in. So here we want pressure P1. So we want to know how much pressure the liquid carries. And we also want to know how fast it is flowing. And at the same time, we want to know its height. Okay. So I'm drawing this pretty wide, but that's just exaggerating. The volume is, well, not volume. The cross section is changing, is gradually changing. So it's exaggeration. So I'm not counting the top as higher than the bottom because the flow is relatively thin enough compared to how much the vertical change is going to occur between 1 and 2. Okay, so over at point 2, we also want to know pressure here, velocity, and also height. Oh, keep going for the 1. Okay, so we want to know these because we want to know how fast it's flowing out, what kind of pressure does it have, and what's the height relationship under the relationship. So let's write the equation out, and then we'll explain how the equation came about. Okay, so on either side the equation, things look pretty symmetrical. Pressure is included, pressure is included. The 1/2 rho is the density of the liquid. 1/2 rho e squared, 1/2 rho e squared of the other side, rho gy. So it's very It's very symmetrical. I can also call this equal to a constant. So the constant is just a constant. It will depend on the pressure, the speed and the height, right? And also the density. Liquid density. All right. So how did this equation come about? Well, here's how we can imagine the equation came out. So first, let's move that P1, P2 over to the left side. So P1 minus P2. And we also want to multiply by a volume. And sorry about the V happening here and also with this. This is volume. I'll just mark that. So what I did was I subtracted V2 so it appears on the left side, and then I multiplied the entire equation by a V, a volume. How large is the volume? Well, it really is irrelevant. It just, you can draw a small box, imagining that enclosing some liquid. And here the same exact volume box. Okay, it's just, I probably should have moved where I draw the boxes. Okay, so there you go, 2 slide boxes. Okay, and if I have that, 1/2 rho times V, that's also volume, then times V1 squared plus rho times V times G times Y1. I think that's getting a little redundant. That's also volume. And the other side doesn't have the P anymore. 1/2 rho V, V2 squared plus rho V, GY2. Okay. So what can we do with the rho times V? Well, rho is density, is mass per volume, and the volume is volume. So mass per volume times volume, right? Liquid density. So I can say mass is equal to density times volume, because density has mass per volume unit, and multiplied by volume, it is mass, right? So that's what it is, it's mass. So everything in parentheses except for that one, right? Everything in the parentheses rho V is mass. And the only thing that's not mass is over here. So we'll morph that into some sort of mass in the next step. So that is plus 1/2 mv1 squared plus mgy1. Well, that starts to look like kinetic energy, right? And then 1/2 mv2 squared plus mgy2. So this starts to look like a kinetic energy of, well, mechanical energy on one side, mechanical energy on the another side. There's an additional term P and V, right? So let's make another change, and we'll just assume that V turns into area and some sort of delta x. Okay, so if this is a cube, then the area is just delta x times delta x, and the volume is delta x times delta x times delta x. So whatever it is, you can turn the volume into an area, cross-sectional area times the delta x, which is along this direction, delta x. All right. So let's do that, and that turns this into P1 area minus P2 area delta x, right? Volume gets replaced. And plus, okay, I'll just write mechanical energy 1, right? This is mechanical energy 2. Mechanical energy. All right, so pressure times area, what exactly is that? Pressure times area should be equal to force, right? Pressure is force per area. So now pressure times area is equal to force, all right? Because pressure is force per area. So I'll write this as F1, force against this small volume, minus F2, force against this firm volume over here, delta x That's the cross, not cross section, the width of the small volume, plus E1 equals E2. And force times distance, this is work. So this is a generalized energy conservation. It says, well, E1 is not equal to E2 because some work was done on the liquid so that it gains this much energy, W amount. So the final mechanical energy is initial mechanical energy plus the work done by the differential pressure of the liquid. So if the liquid doesn't change pressure along the entire tube, then there's no work done on the liquid. So E1 will be equal to E2, and what could happen is the liquid is just flows like free fall, right? Mechanical energy on one side is mostly kinetic energy on one side because it's a lower height. Mechanical energy on the other side is probably mostly potential energy due to gravity, and it flows more slowly because it gets to a higher height, right? So that's very understandable considering the liquid just like a continuous amount of small individual masses that we can discuss. So something goes from a higher height comes down to a lower height with higher kinetic energy but lower height, right? So that's that. But liquid can also be pushed. So there's this work done is done by the differential pressure between two sides of the pipe. Okay, so that is where Bernoullis equation comes out. It is an application of energy conservation. Okay, so remember energy conservation, we're not counting friction because it is ideal fluid, there's no viscosity, so no friction. We're also not counting anything that the fluid can compress and somehow store energy due to compression because we took that away. We said the fluid was incompressible and there's no curls around the fluid to actually contain energy. That's kind of rotational kinetic energy of fluids. No, there's no such thing, so we don't have to include those into the E1s or E2s. So that's why they start to look just like what we have encountered before, just rigid bodies and translational kinetic energy only. Okay, so that's how the equation looks like. I'll give you an example of how to calculate something, such as if you had a water container like I have here, and say you have your container springs a leak on the side. There's a hole there, and maybe that's purposefully put there is where the tap is, for example. And how fast does water come out of that hole? So let's start that question. Um, we'll draw a water tank. Okay, so let's say the water tank has a total height of capital H. May or may not be relevant because I don't have to fill it to the top, but I do. So it's filled with liquid. Okay, it's all filled up. And there's a hole here at the height of lowercase h. And the hole is drilled horizontally. So if this were a tap, this were maybe not a proper tap. Maybe the tap actually fell out. The hole was remaining. It's a horizontal hole. So water will come out and splash here on the ground. So that's the extent of the question here is how far did it splash away from the container, right? So we'll all have the variables h, lowercase h and d, things like that. And we'll assume that atmospheric pressure is P0. Okay, we don't really have to care exactly about the pressure, but we want to define that as P0. Okay, so now the fluid starts to flow. And how do we use Bernoullis equation to solve it? Well, to use Bernoullis equation, we need to define two separate places. And of course, this is a 2, right? This is where the flow tube is going to meet air. And where's 1? 1 can be this entire surface here, 1. All right, so we can imagine there's kind of a flow tube. Oops, missed it. A flow tube, something like that, that just kind of all flows into that hole. And we understand that as much as water flows out, the water level over here is changing very, very gradually because the hole is really small, and this cross section of the water tank is large, right? So we assume. So this water surface is constant during the flow. So we can at least find out the speed, initial speed. If not, say if it has gone down a little, and then the flow probably gets a little less fast, right? You splash a little closer, but that's okay. At least we can find out the initial splash zone right here. So that's assumption, and we also assume. Hmm, the pressure of water at the horizontal hole is at atmospheric pressure because it's flowing out, meeting the atmosphere. So if it has higher pressure, then it will actually expand into a broader stream. But if it doesn't do that, then it has already equalized with the atmospheric pressure. So at 1, right here, so we have pressure. Pressure 1 is actually equal to atmospheric pressure because this surface is open to the air, right? So pressure P0 right here. And V1 is approximately equal to 0. And because surface is large compared to the whole cross-sectional area. So we have volume, we also have Y is a constant, right? Constant. And at 2, we also assume that pressure is about the atmospheric pressure, and the V2 is no longer 0, and it's fast. And then Y2 is equal to H. Okay, this H doesn't change. All right, so now we have conditions at both ends of this flow tube or flow pipe, and we can use Bernoullis equation. So using Bernoullis equation, P1 plus all these equals P2 plus all these, and P1 is equal to P0 atmospheric pressure, and then rho times 0. V1 is near 0 because the surface drops really, really slowly. And plus rho g, y1 is height h, that doesn't change. And the other side has pressure also open to the air atmospheric pressure, plus 1/2 rho v2 squared plus rho g y2. Okay, so this is 0. That subtracts that away. So all we have is rho gh. This is like mgh, potential energy, equal to, so mgh, a different potential energy, and the rest goes to kinetic energy. So that's just like water free falling from here all the way down to that height. Same idea. It just kind of goes in a curled surface, and with no friction, it does the same thing, like a water slide on water, and water is on the water slide. So we have the rows we can divide out. So divide out the rows. We have GH equals 1/2 V2 squared plus GH. So let's replace that by H now. And the 1/2 V2 squared is equal to G height minus height. So we can find out V2 is equal to twice G height minus height square root. Okay, so I only have 1 minute left. I can't really solve the exact d here, but now that we have this velocity, we can consider this as a projectile now. All right, so consider this as a projectile. What we can do is to solve this with a projectile having a horizontal launch speed. And let's think about this. The distance here. Can we actually drill a hole that makes the farthest distance? Say that's a game. You're trying to drill a hole so that the water can splash as far as it can. So how do we do that? Well, to do that is no longer just the speed anymore, right? It also concerns the height, right? So we'll have to find out the real distance here, and then find out how the distance can be maximized. So let's find out the distance here with a projectile motion problem. And the projectile motion problem, we can set up x0 is equal to 0, x is equal to d. So horizontal motion is d far away. V 0's x velocity is this v2 that we just found. And v0y is 0. We have a horizontal hole, so the water comes out horizontally initially. And vy, we don't really care about this, but that's okay. We don't need to solve it either. And we also have the, let's see, the d is supposed to be an unknown we're solving. And here's another unknown. Here's a t is equal to some unknown time. How long does it take to splash across, right? So our equations are x equals x0 plus v0t plus 1/2, v0xt. And this turns into d is equal to x0 is 0, v0t is v2 times t. So as soon as I find t, I can find the distance. Okay, y is equal to y0 plus v0yt minus 1/2 gt squared. So starting with an h, lowercase h, initially no velocity in y, minus 1/2 gt squared. And y is also equal to 0. Let's see, y0 is equal to h, y is equal to 0. Okay, so what this equation gives us is h is equal to 1/2 gt squared, or 2h over g square root equals t. So now I can take t and plug it into the d. So let's scoot to the right side. D is equal to all these things, v2, 2g, h minus lowercase h, and the t is also inside of square root, so 2h lowercase over g. Okay, so we can get rid of these, and we can combine the factors of 4 h, capital H minus lowercase h. So that's the total distance traveled. It makes sense because h is a length unit, and then h minus is also length unit. Square of the length unit taking square root, that's a length unit. So what is the maximum distance that you can get from this? If you increase the height, this factor increases, but this whole factor decreases because you increase this negative h, right? So it ends up being that the max is when d with lowercase h equals 1/2 the uppercase h. So you drill a hole halfway between the water surface and the bottom, and so this will be equal to 4 h over 2 h minus h over 2. So that's a half h. That's half h. So the halves quarter 4, right? So that's equal to h. That's kind of weird. The height of the water surface is the maximum distance that the water jet can travel. All right. Thank you so much.